Hey everyone, Mr. Skelton here, back at it. Lesson 3, Unit 9. Today we're going to be talking more about conditional probability. We actually started to have a little discussion about conditional probability in Lesson 2. And today we're going to get into some more detail with some tougher questions. Just kind of make your brain hurt a little bit. If you have good number sense about you and if you can kind of visualize situations, that can be helpful in this lesson. There's a formula that I'm going to give you here in the second slide. I think sometimes that formula can be detrimental. Not detrimental, that's probably the bad word. Sometimes I just don't think using the formula is the best idea. I think sometimes creating a visual can be helpful, and I'm going to do that in a few of the examples for you today. Okay, so just a refresher on conditional probability, and we'll kind of go through this again. Conditional probability is the probability of an event happening given that something has already taken place. All right, so if you remember, I gave you this formula in lesson 2. Let's talk about it real quick. So the probability of event A, that's what we want to have happen. What we want. Okay? What's the probability of event happening? This line right here means given, the word given that B has already taken place. Okay? Now, this right here is quote unquote the formula. And this means intersection, that symbol. A lot of people just say and, use the word and, the probability of A and B divided by B. What we're doing is we're narrowing our sample space. Okay? With basic non-conditional, when we say non-conditional, it's non-conditional. Non-conditional probability is like, what's the probability that I roll the number 4 on a number die? Well, how many 4s are there? There's 1 4. How many total outcomes? There's 6. So the answer is 1 6. That's non-conditional probability. It's not based on something already taken place. So it's real important that you understand that the denominator is always going to be what has already occurred. All right? And I'll try to remind you of that as we go through the notes. The intersection doesn't necessarily mean you're going to be adding numbers together to get the numerator. You're not going to be timesing numbers together to get the numerator. It's just going to be the intersection of the two probabilities, and I'll kind of show you with some examples, and some of them are easier than others to kind of define that intersection point. The first one is pretty easy to understand, the intersection spot, because you actually see it and it actually tells you. So we're going to use a Venn diagram here in this first example. It says in a group of 100 students, so I'll just draw a rectangle, and I'm just going to put 100 students outside of it. 40 of those 100 are taking algebra. Oh, I'm going to put probability, I'm going to put A for, I'm going to put a 40 there, so that's representing my algebra. And 30 are taking biology. So B for biology, A for algebra. And 20 are taking both. 20 are taking both. Okay? If a student chosen at random is taking algebra, what is the probability that he or she is taking biology? So how can we take apart what this is actually asking us to find? If a student chosen at random is taking algebra, what is the probability? So this is what we want. What is the probability? That's what we want, that he or she is taking biology. So what's the probability of a student taking biology given they're taking algebra? That's what that translates into. If you go with the formula, right, it'd be the probability of the intersection of B and A given that A has already taken place, right? It already says if a student chosen at random is taking algebra. So this is what the formula would look like. Now with this Venn diagram, I'm going to actually go back to kind of give you what we're looking for in this Venn diagram according to this. So if I just put 2 circles in here, and this is probability of A, this is the probability excuse me, of B. What's the probability of A taking place given B has occurred? So I'm actually going to shade B because B has already occurred, right? So I'm just trying to show you the visual components here of this Venn diagram. What's the probability of A taking place given that B has already occurred? What are we looking for? We're looking for this intersection of A and B. That's why we refer to it as intersection, because B has already taken place, but we want to know what the probability of A is going to be given that B has already taken place. So the probability that A takes place given B is just this intersection, and that's kind of a visual representation kind of that formula. So I wanted to show you that prior to getting into this problem. I kind of forgot, so I went backwards just slightly. So now let's crunch some numbers and put this all together. So off to the side, I'm just going to, I don't want to do too much here, but kind of bring you back to non-conditional probability as well. So for example, like the probability of just a student taking algebra, what would that be? Well, 40 out of the 100, right? 40 out of the 100, that's 40%. What's the probability of just kids taking bio? 30 out of 100, 30%, okay? But what we want is the probability that B intersecting with A, which is already given to us, they told us is 20. Where is B intersecting with A? Right here, over that A is taking place. So the probability of A. Well, we already know the probability of A. It's 40. So really what happens when we go to crunch this formula and put numbers into it, the intersection of B and A, or B and A, was basically 20%, right? I forgot to do that. That would be basically 20 out of the 100 did both. That's 20%, so 0.2 over 40% of, because that's what the percentage of kids taking algebra. And if you do that real quick, most of you can do this in your head, but I'll show you on the calculator. Divided by 0.4, you're going to get 50%. Okay, 0.5. So 50% is the probability that that person is taking biology when taking algebra. So that's using a Venn diagram. Now we're going to get into a kind of a trickier problem here, and I'm actually not going to use a Venn diagram because it's kind of, I think, counterproductive in getting us to the answer we want. So here's the situation. What is the probability of a couple having two girls, so two children, both girls, if we know, so given that, if we know is code for given that at least one of the children is a girl. All right, so I need a visual. What are my options here? Kind of like a Punnett square, right? Two children. Could be boy, boy. Could be girl, girl. The oldest could be a girl, followed by a boy. They could have had a boy first, followed by a girl. And that's really it. Those are your choices, okay? Because it doesn't really matter if they had this boy first or second. It's still a boy, boy, first or second, oldest, youngest, still girl, girl. So what's the probability of a couple having two girls, okay, given that at least one is a girl? So if you wanted to go here, A would be two girls, given that one is a girl. So this intersection part is a little tricky here, right? So for me, what is the probability? So we're looking for that top part of the fraction here, of the intersection of the two. Well, what is the probability of a couple having two girls if we know that at least one of the girls, or one of the children, is a girl? That's the same situation, because if they have two girls, girl, girl, and at least one of them is a girl, it's one and the same. So it's really just basically 1/4. Probability of having two girls, 1/4, the intersection of those two, if we know that at least one of them is a girl. Now, that bottom fraction is a little tricky here. If we know that at least one of the children is a girl, well, look at the 4 boxes. How many of those boxes have a situation where one of them is a girl? 1, 2, 3. So that would be 1/3, right? Or excuse me, 3/4. 3 of them, 3 of the 4. So it should be 1/4 over 3/4. If you solve that, got to multiply by the reciprocal, you would get 4/12, which is 1/3. 1/3 would be your answer. Okay? I know that's kind of difficult to do. For some of you, it's going to be really easy. Some of you just have that math brain. You have that. You can figure out that probability stuff in your head, and you can go from there, and it'll work for you. Okay? So here's a similar situation, just slightly different. I know I have the answer here in the corner. It's an old PowerPoint. What's the probability of a couple having two girls if we know that the oldest child is a girl? Again, I like to see my options here. Girl, girl, boy, boy. Oldest is a girl, youngest boy. Oldest is a boy, youngest girl. So what's the probability of a couple having two girls? So if we know that the oldest, and you don't have to write out the formula every time, like you don't have to write P, A, given B, and write out the formula like P, A, union B, intersect B over probability B. You don't need to do that every single time. So you can just figure out the answer, right, and go from there. You know it's going to be a fraction. So the intersection of A and B, again, very similar. What's the probability of a couple having two girls? If we know that the oldest is a girl, that's still going to be 1/4 because it's one and the same. On the bottom here, that the oldest is a girl is going to be 2/4. Why is this 2/4? Why is the probability of given that B that the oldest is a girl? Well, because in girl, girl, that's the oldest. Girl, boy, that's the oldest. So 2 of the 4 boxes have the oldest child being a girl. You go to solve this, and you get 4/8, which is 1/2 when you reduce. Okay? I know those are 2 challenging ones. The third type of question you're going to see probably on your homework is something using a frequency table. We did some frequency tables, I believe, in lesson 1. So the first thing I want you to do is just fill in the missing numbers. You have this is obviously talking about education, high school diplomas, bachelor's degrees, doctors and masters, and males versus females. So just some basic calculation. Total's 28 if we're going by column here. 28 minus the 16 gives us the 12. Add these 46 plus 51. We're going to get 97. Let's see, total is 6, 3. That means this has to be 3. Then we got to find some totals here. We got to go across. So 12 plus 51 plus 3 females. There's 66 total females. Okay, and then we would do the same exact thing for the males. We go across for total amount of males, or total amount of people total, or yeah, total totals. So 28 plus 97 plus 6 is 131. So we have 131 total people in this situation. Okay, now that we got the table filled, the frequency table filled, let's do some conditional probability. So find the probability that someone has a bachelor's degree given that they're a male. Probability that they have a bachelor's degree given that they're a male. Okay, so what's the intersection of that? If you wanted to use formulas, what's the intersection of the probability of, or what's the intersection of the probability of if it's a bachelor's degree given it's a male? Bachelor's degree given it's a male. That would be 46, right? Probability, bachelor's degree male, given that it's a male, okay? Which is a total of 65. So we should have 46 divided by 65, which is going to give me 0.707. If you move that over, that's 70.7% probability. Okay. Part C, probability that it's a female given they have a master's degree. Probability that it's a female, I put F for master's degree. So it's the intersection of female and master's degree over master's degree. Probability of a master's degree. So not so bad. Where's the intersection of females and master's degree? Right here, 3. Right there. Given that it is a master's degree. Total 6. 1/2. Done. 50%. If you want to make it a percentage. Okay? All right, there's the lesson on 3 conditional probability. A few different examples there of some problems you may or may not see down the road. Look forward, as always, to working with you in class and answering any questions you might have. All right, take care.